Hello, my name is Chloe Schmenti, and today my goal for these videos is to teach you how to do some of the things that I struggle with in my pre-calculus class. So I'm hoping that these videos coming from a fellow pre-calculus student will help you a little bit more with your understanding as I try to touch on some of the things that I was struggling with that I just needed a few little hints. So hopefully these will help you. And the first thing I'm going to focus on is exponential functions. So here's the definition. An exponential function is a function with base b that has the form f of x is equal to a times b to the power of x. X is any real number, and I'm just color coding them to make it a little bit easier for you to see later. Now, x is any real number, and a and b are real number constants. So a cannot equal 0, and b cannot equal 1. So moving on to how to graph the exponential functions. So the first thing is, here's some of the things that you're supposed to be looking for when you're graphing the functions. So you're looking for the domain, the range, intercepts, asymptotes, and end behaviors. So my example is going to be f of x equals 3 to the power of x. The first step would be to plug in values for x. I recommend -4 to +4. So first thing you're going to do is create a table with the values -4, -3, and so on, all the way to +4. Now, just for the sake of time, I'm doing -4, -2, -1, 0, 2, and 4. It'll still give me a pretty comprehensive idea of what the graph is going to look like. In some cases, your teacher may not ask you for specific points. I prefer to have specific points because that's just the way I am, but some teachers just ask you to do a rough sketch and show the end behaviors. So you can see when our x value is 0, that is when it hits the x-axis, which makes it an intercept. So our intercept is at 0, 1. So when you're going to graph it, one of the easiest places to start, I find, is the intercept. Just makes it a little bit easier to know which points are where. So number your graph, 1 through 4 and -4 to 0. You're going to plot your points, and you're going to put a rough sketch in the line of the points. So you'll notice that the y never hit 0. I can keep going to -5, -6. It's not going to hit 0 or the x-axis. So that would mean that our asymptote is at y equals 0 or the x-axis. Our end behaviors, you can see the directions of the two arrows. So as x approaches positive infinity, y approaches positive infinity as well. So as one gets bigger, the other gets bigger. So our domain is, because the asymptote is y equals 0 or the x-axis, there was a little typo on my part, all real numbers is going to be our domain. The line never goes below the x-axis, so our range has to be all y's greater than 0. So now that we've learned how to graph it, let's move on to transformations of a graph. So here's our problem. Use the graph f of x equals 2x to describe transformations. So our three problems, the way this is phrased means that your 2 to the power of x is going to be your parent graph, and A, B, and C are your transformations. So our parent graph is going to be in red, and our transformation is going to be in blue. So the +1 next to the x expands the graph vertically. So our new transformation is going to be 1 unit stretched vertically. And then when you see our 2 to the power of negative x, that is going to reflect our transformation across the y-axis. So they're like mirror reflections. They mirror each other. And then our -3 to the 2x, negative 3 times 2 to the power of x. That negative in front of the 3 is going to reflect our problem over the x-axis. And then it expands it vertically by 3 as well. So the negative itself reflects our problem over the x-axis. But the 3 expands our graph vertically by 3. Now, most real-world applications of exponentials will use the base e, also known as the natural base. So e, when plugged into a calculator, or just the e is always constant. Our e is always the same number. It's about 2.718. Now, e to the x so our natural base exponential function is f of x equals e to the power of x. It's important to know that this e to the power of x does have the same properties as our regular exponential function. So our a times b to the power of x. It's going to have the same properties, including our transformation rules. So now, logarithmic and exponential functions. A logarithmic and an exponential always are taught together. A logarithmic function is the inverse of an exponential function, and vice versa. So you can see that our logarithmic functions are the inverse of our exponential functions. And these formulas, using just the variables, you can plug your logarithmic function and your exponential function in and find the inverse. So now that we have that formula, we're going to take our problem. So our example problem is log base 3 of 81. So we know that our b in the exponential function is going to be 3. Now, our 81 is not, because it's log base 3 of 81. So what we need to do in order to solve this is, you notice that there's a rule where when the base and the x are the same, they cancel out and you're left with that 4. Or you can use our inverse, and your log base 3 of 81 is going to become 3 to the y equals 81. Then 3y equals 3 to the power of 4. That cancels out our 3's and leaves us with y equals 4. Now, our second example problem is where it gets a little bit more complicated, but it should still be relatively easy to grasp. So log base 5, and then we have a square root of 5. So you're going to set it equal to y. So our exponential is going to be 5 to the power of y equals the square root of 5. Now, inside. So our next step is 5 to the power of y equals 5 to the power of 1/2. So that 1/2 is because the 5 is to the power of 1. And a square root always has a 2 on the outside. So that's going to give us our 1/2. Now those 5's cancel out, so we're left with y equals 1/2. Now moving on to some of the basic properties, we have log base b of 1 equals 0. Log base b of b equals 1. So these are the properties that we demonstrated previously. And then we have the inverse properties. So part of what had confused me when I originally learned these inverse properties, and what I'm hoping to help you avoid, is our log base b of b to the power of x, and our inverse b to the power of log base b of x equals x, comma, x is greater than 0. So what that means is that our x has to be greater than 0. So a good example problem of that is, or log base 5 of 5 squared is going to equal 2. Now, our two good example problems is log base 5 of 125. So 125 can be turned into 5 to the third, which is 125. So that cancels out our log base 5 and our 5, leaving us with x equals 3. And then when we have 12 to the power of log 12, 4.7 means that we're going to have our x is equal to 4.7. Now, it's important to know, and this is something that I really should have known before I started my pre-calc, but it was a total game changer as soon as I learned that this was why some of these rules did apply and didn't apply. So a log with a base 10, so log base 10, is called a common log. This is usually written without a base, which that was the part that had confused me. And a log with base e, or log base e, is a natural log. So log base e is oftentimes put in a problem as ln. So when you see ln, that means log base e. So when you do ln of e to the power of 0.73, that rule that we previously applied also applies here. So that cancels out our log base e and our e, leaving us with x equals 0.73. Now moving on to how to graph a log. So let's say we were asked to graph log base 3 of x. First, you're going to choose values to plug in. Once again, I suggest -4 to +4. Second, before plugging in these values, you have to find the inverse. So the inverse of log base 3 of x is going to equal 3x. 3 to the power of x, Now you're going to create your table and plug in your values. Now you are going to take your parent graph, which is the 3 to the power of x. Once you have this, there is a line that goes in between, which is where y equals x. So, for example, your coordinates would be 0, 0, 1, 1, 2, 2. So now you're going to take your values that you have for your 3 to the power of x. So your 0.01, 0.11, 0.33. And you're going to reflect those points over that line. Now, once you've plotted your points, you can find your domain and your range. So the range for all logarithmic functions when graphed is all real numbers. Your domain for this one is all x's greater than 0. All y's greater than 0. My asymptote is going to be my y-axis. You notice that the logarithmic function never crosses over that y-axis. It has no intercept on the y-axis. So our end behaviors are going to be which directions the ends of our curve are pointing to. So as x goes towards positive infinity, y also goes towards positive infinity. Now, our properties of logarithms. Just take a minute to look at some of these, and then I'm going to just put them up in the corner as we continue on with our example problems, just to reference when needed. So one of the common things you'll get asked is to express each log in terms of a number. So, for example, this one, express each log in terms of ln of 2 and ln of 3. So our first problem is ln of 54. So we can, for the moment, pretend that the ln is not there. So 54 can be equal to 2 times 3 to the third. Now add our ln's back in and put them in front of those two values. So ln of 2 plus ln of 3 to the third. Now, using one of these properties, we can take that exponent on ln of 3 to the third and put it in front of the ln. So now our problem is going to be ln of 2 plus 3 ln 3. And that will be our expression. Now, when you look up at our quotient property, so ln of 9 divided by 8, our ln is going to be, our first one is ln of 9 minus ln of 8. Let's just put the quotient property in first before we even begin to express each log in terms of ln of 2 and ln of 3. So we know that 9 is 3 to the 3 squared, and we know that 8 is 2 cubed. So now we can use that same power property and move the exponents in front of the ln's. So 2 ln of 3 minus 3 ln of 2. It is minus because, as shown in the quotient property, the division makes it minus while multiplication makes it plus. So that is our expression. And then we're going to use properties to evaluate / simplify our logs. So when we have log base 4 to the fifth root, log base 4, fifth root of 64. So when we use the, so we know that there is an invisible 1 in that fifth root. So we're going to have log base 4 of 64 to the 1/5 power. This way we're getting rid of that square root. Now we can take the 64 and, like we had done previously, turn it into log base 4 of 4 to the third. We can do log base 4 of 4 to the power of 3. And then you put that in parentheses, and your 4 to the power of 3 is to the power of 1/5. So we have to multiply those two together, and we get 3/5. So now we have log base 4 of 4 to the 3/5, which means that our 4 and our 4 cancel out, leaving us with just our 3/5. Now, using properties to expand each expression. So let's say we have log 12, x to the power of 5, y to the power of -2. So now we're going to take our log and put it in front of each individual component we have. So log 12 plus log x to the 5th plus log y to the -2. Now, we can use that power property once again and move our powers in front of our logs. So log 12 plus log x to the fifth minus log 2 log y. We can also do that to our x to the fifth. Now, let's use it to expand a little bit more complicated of a problem. So, ln of x squared divided by square root 4x plus 1. So, we're going to take our ln and put it in front of each of our components. So, because it's a division problem, we subtract. Ln of x squared minus ln of the square root of 4x plus 1. Now, we can use that same property we used to get that 1/5 and apply the same thing here. So, our next step is going to be ln of x squared minus ln of 4x plus 1 to the 1/2 power. Now, there's an invisible 2 inside a square root, hence square root. And there's always an invisible 1 inside the square root. This is part of what I had struggled with understanding and why I didn't understand some of the answers to problems. So we can take this, we can use that power property again and put the power in front. So 2 ln of x minus 1/2 ln of 4x plus 1. Now using properties to condense, so doing the opposite of what we just did. We have 4 log base 3 of x minus 1/3 log base 3 of x plus 6. So we can reverse our power property, and we're going to take our numbers in front and turn them into the exponents. So just to start off pretty simple, log 3, we know that subtraction means that it's going to be a division. So log base 3 and then x to the 4th divided by, and that 1/3 clues us into the fact that it is using a cubed root. So our 3 is going to go right in between that little dip. And so our problem is going to be log 3 x to the 4th divided by the cubed root of x plus 6. Now, how to do the change of base formula. So here's the formula. I've color-coded it just to make it a little simpler and easier to process. I'm going to put that up in the corner while we do our example problems, just as a reference. Or if you're doing your own problems and these are just, homework help videos. So we have log base 1/2 of 6. So we're going to take our x and put it on the top like the formula shows. So log of 6 divided by log of b. So our log of 1/2. Now you can use your calculator log button, and you'll plug in your values, you'll press the log button, put in the parenthesis the 6, and then don't forget to close the parentheses and do the same for the bottom. That gives you a negative 2.58. I hope these videos really helped. I really wanted to help people in a way that I could because I do struggle in math, and I was really trying to find a good way to help fellow students. So I'm hoping these videos helped you understand even a little bit better. Thank you so much. Bye. Our end behaviors, you can see the directions of the two arrows. So as x approaches positive infinity, y approaches positive infinity as well. So as one gets bigger, the other gets bigger. So our domain is, because the asymptote is y equals 0 or the x-axis, there was a little typo on my part, all real numbers is going to be our domain. The line never goes below the x-axis, so our range has to be all y's greater than 0. So now that we've learned how to graph it, let's move on to transformations of a graph. So here's our problem. Use the graph f of x equals 2x to describe transformations. So our three problems, the way this is phrased means that your 2 to the power of x